Hello, can you hear me? Yeah. I'm fully aware that I'm the only thing that is standing between you and the rest of your weekend now, so I will try to keep it short and snappy. My name is George, as you heard, and yeah, you heard all of that, so let's just crack on. I will be talking about what is the difference between understanding your data and making predictions about your data. I will try to characterize when we actually need to do it, because I think it's not always the case. I will try to characterize what is understanding, how we generate it, and what are the tools that can help you with this sort of task. So this might be obvious, but I think this difference is often underappreciated. The fact that you can model something doesn't mean that you understand how it works. The classic machine learning models usually just give you a prediction of what is the value of your parameter supposed to be in the future. In better case, they give you probability distribution over that parameter. And this is fine, I would say, maybe even in most cases. But there are very many cases as well in which this is just not good enough. As I put down there, classic machine learning models are often called black box because you don't see inside, it just throws numbers at you and they give you prediction. We often call explainable AI white box systems because just because it's a contrast to black box, really. But the idea is that what you get out of it is some sort of underlying mechanism that is driving your data. So let's start with the reasons why you would need explainable AI. In my job, I often inform strategic decisions of large companies, and when there's a board meeting and they are trying to get some insight into a strategic decision that is data-driven, they don't care about what your neural network says. They can't care less. They don't understand what it is, and they just don't want to hear it. You need to give them a reason, and then they work with it. So in this sort of situation, this is one of the situations in which you may need to be able to explain what is going on in your model. The other one is justifiability. So whenever your machine learning model actually affects people's lives, you have to be able to justify your decision. There is a famous example that is the schools in New York State. They used neural network modeling for evaluating teachers. They based some layoffs on this modeling exercise. It was a disaster, a class lawsuit, big compensations, and loss of credibility as well. Also, in the GDPR, it is now in power across the European Union, that grants all people the right to have an explanation if they ask for it when you make a decision about them based on data. So that's another reason. Yet another reason is discrimination. In machine learning, we often replicate discrimination that was committed before by human actors and that is included in our data sets. Now, if you model something with a black box, it's hard to find out that you are actually committing discrimination. I'm not saying that having everything explainable is a guarantee, because often discrimination works through kind of proxies such as postcode or profession, things like that. But it lets you rule out some of the things that you really don't want to influence your decision making. Related to this are feedback loops that are particularly dangerous when they go together with discrimination. So let's imagine a case from a lending example, really. So imagine that you are a member of a group that was discriminated against, and therefore you are evaluated as having a higher risk of not paying back your loan. Therefore, the loan that you will get will be of higher interest. Therefore, you are less likely to pay it back because you are paying back more money. If you don't think about what you are going to do, about how your model works, you will not be able to identify problems like this. The other, and this is actually very theoretically interesting for me, is facilitating improvement. If you have a black box model that predicts, let's say we are dealing with HR now, it predicts whether someone will leave the company or not. And that's great. It will label those employees, but what do you do with them? Do you fix the problem? No, because you don't know what is the problem. You only know that they are likely to leave. So you can try to fix it somehow, but it will likely not be the way. You will likely not be fixing the problem. You will be just kind of raising their salary or something like that, trying to convince them to stay otherwise. If you actually try to model the problem in a way that is explainable and understandable, then you can tell the HR manager what is the problem and they can fix it. And this is a really significant advantage that I see in this. The last reason why I think you should often use explainable methods in AI is overfitting. So I didn't make this up, it's real. If you would be training a black box machine learning model on this sort of data, it will pick up that relationship and it will use it for predictions. If you instead try to understand what is going on and this comes up, you just immediately can spot that this is rubbish. And you will take it out of your model and your model will not be using this for its forecasts. And the useful way of thinking about this is your experience of being human in this world is some sort of extension of your data set. It's a natural prior that you collected through your experience that you can use, and that is not accessible to your machine learning models. I think this is very well illustrated by this figure. So this piece of research took a number of studies in social science, and they basically went out in the street and they were asking people how likely the people, laymen on the street, think that the proposition of this piece of research is true. So is this hypothesis real, true, or not? And that then very well correlates with whether those hypotheses indeed turned out to be true. So layman guesses, common sense actually works to quite significant degree, and there is no reason why we should give up on it. It's often useful. So how do we get understanding of our data and what the understanding really means? It's usually formulated in forms of hypotheses, as A causes B, but how do we generate them? The classic inductive model of science that was first defined by Francis Bacon is basically kind of trying to understand small elements and then putting them together into larger blocks, such as let's look at electrons and protons, how they work, then we can go further up, we can start to understand how molecules work and go up and up and up. And this is great, and it has moved us very far during the centuries. But what our job is, as data scientists, is looking into very complex systems. And complex systems have actors that are interacting with each other, and they are more than just the sum of their parts. Let's think about an example. Let's consider a hypothetical task that you want to model a market, and can you start with psychology of individual human actors, put it together and say what will be going on in the market? That just wouldn't work well. I mean, might be useful to some degree, but really won't get you far. So what we have to do instead is deductive, or maybe rather abductive approach to science, to generating hypotheses. So abductive approach was first defined by Charles Peirce, and what it means is that you look at the data, and while looking at it, you try to figure out what might be going on. And this is really important, this idea that you look at the data. Because sure, you can approach your complex system and just say, I will just test whether there is a difference between those two conditions or not. If I find significant difference, there is a difference. But there is a problem. And the problem is very well illustrated by this. And these data sets that you are looking at all have identical mean and standard deviation at 2 decimal places. So if you will be comparing these data sets with just the hypothesis that there is a difference in mean and standard deviation, you will conclude that they are all identical. But if you look at it, you can generate hypotheses that will let you distinguish between these data sets very reliably. This is an idea that was first proposed by John Tukey in the 70s, and what we do as Illumer is basically an extension of that, really. So in practice, this is a Boston housing data set. That is a data set that is describing a number of houses in Boston, and each house has a number of attributes, size and location, and also value. And what we are trying to look into here is what makes houses more valuable. So I have my data set, I look at it, and I see that there is a group of houses that they are clumped together, so they create a cluster, so they are presumably similar to each other, and they also tend to have quite high value. So what I do with this sort of picture is I label this as my region of interest, and I try to figure out what makes these houses special. And this is a fundamental difference from kind of the most typical approach to machine learning. I'm not trying to predict the value, not building a regression model. I'm not even building a classifier to classify the more valuable houses from the less valuable houses. I have labeled an arbitrary, well, kind of arbitrary chunk of data that naturally holds together because there's something in common. It's an interesting pattern, and then I'm trying to explain that pattern, and that can get me quite far. But you might be asking, how come that the data is 2D? Because Boston housing data set has around 40 variables. And this is a crucial problem for exploratory data analysis, for looking at your data. You have to reduce the dimensionality, because all the problems that we are dealing with these days have very high dimensionality, or they have been solved. So before I get into how to do dimensionality reduction, I will try to kind of illustrate why you would be doing this a little bit more. So other examples besides property value is a great stuff that we did for EasyJet and Banco Sabadell was doing customer segmentation. But if you look at the data, then you can spot things that you wouldn't get otherwise. So for instance, if you run a clustering algorithm across the data set, you get some clusters, it's great, but often very small clusters will get absorbed into larger ones. And they might be interesting. Unless you look at the data, you can't tell that they are interesting, and you can't sort of push the threshold a little bit for that cluster and actually look at it. Those are things that will just get lost. We've also looked into aerodynamics for Williams F1, looking in what is the relationship between the shape of front wing, and then there is a vortex of wind coming from the front wing on the body and creating downforce on the body. This is usually would be modeled by computational fluid dynamics, but it's too complex of a flow, so the error from computational fluid dynamics is too high. And we were looking at the data from the pressure sensors across the car and how that is related to the downforce, and we were able to identify relationships between the shape of the front wing and the downforce on the body. And this is a very important example because knowing this allows for improvement. If we were just labeling that these shapes are better than others, then we have no information about how to improve the geometry. Very similar example are innovations on products. We did this for Unilever and for Mintel, Mintel is a very large kind of customer survey agency. We are looking at products being introduced in the market and intention of customers to buy these products, and we were able to give them reasons for what makes a product successful, which again allows you to devise successful products. Okay, so let's go back to exploratory data analysis and dimensionality reduction, which is the crucial bit here, really. So you want to see your data, but dimensionality is too high, because unfortunately our limited minds can only perceive 3 dimensions. There are good ways and bad ways how to decrease dimensionality. The simplest one that I can imagine is just keep first 2 columns, throw away everything else. You have 2-dimensional data set. Look at it. It's probably a bad idea, and the reason why it's a bad idea is because with overwhelming likelihood those 2 columns will not be capturing what is really interesting about the data. And so now I will define a good way of reducing the dimensionality. For this definition, we need to think about a new concept. I will call this extrinsic space. Extrinsic is a space that we observe. So if we think about an example of weather, for instance, extrinsic space are the measurements from all the weather stations. It's temperature, humidity, and whatnot. Then we have an intrinsic space, which is the underlying causes for those readings. So that's how air moves across continents. That's the physics of weather. The most interesting way of reducing dimensionality of data would be to reveal this intrinsic space, because that would just explain all of the data in the best possible way, and you would just end up with literally the laws that are governing the phenomenon that you are studying. So we will be aiming to get as close to that as possible. And this is often called manifold learning, because manifold is a term for multidimensional surface, and the idea is your data lies on some surface, and that most simple surface that you can find that is the best description, right? Most condensed. So what we do is often called topological data analysis, but before I will get into that, I will talk about non-topological methods of dimensionality reduction. I guess everyone knows PCA. And PCA is a good example how a method of dimensionality reduction can be bad. Because the crucial assumption that PCA makes is that the relationship between the intrinsic, the fundamental space, and the extrinsic, which is the space that we observe, is linear. I'm not aware of any relationship in the nature that would be actually properly linear. So whenever the relationship is not linear, PCA will distort your data. Then I will go actually to the end of the list. TSNE, that is a pretty good and very popular method of reducing dimensionality. The assumption it makes is that the distances between points in your data set are t-distributed. And we will see in a little bit what that actually does to your data. Other methods are isomaps and Hessian eigenmaps. These assume isometry, and let's talk about that. Isometry is a concept that if you have an ordered distances in your data set, so AB is smaller than BC, and this is what you observe in your extrinsic space, this order has to be preserved in the intrinsic fundamental space. But if we accept the notion that a lot of what is going on in the nature or in your data set is highly nonlinear, this can be broken, and that is what I'm showing at the bottom. In the, which one is it? In the intrinsic space, A to B is smaller than B to C in this example. But because the intrinsic space is a highly nonlinear transformation of extrinsic space, the relationship is inverted. And what this does to your data points is that it mixes them up when you assume isometry and it is violated. And this is really the driving idea behind topological data analysis. Topology is a branch of mathematics that deals with elastic transformations. So what we see up there is demonstrating elastic transformations. From the point of view of topology, all this object, donut and cup, are the same objects, really, which has some disadvantages, but a large advantage as well, as you will see. The consequence for data analysis is that we consider only the distances on very small scale as meaningful. And this sorts out the isometry problem to quite large degree, because any nonlinear transformation, if you look at it at very small scale, should look like linear, local linearity. What this means in plain words is that when we are trying to say something about this point, then this point is useful because it's close, so that is a meaningful comparison. The points over here are not useful because there has been so much nonlinearity happening between those points that there is just no meaning in that comparison. And this has also an important implication for the measures that we take, because the measurements we take are in arbitrary units. There is not necessarily any relationship, any straightforward relationship between the distance in meters of something and the fundamental thing that was going on in your data set. So what is the impact of using this or not using this on your data? The left panel shows a 3D point scan of a rabbit. The middle panel shows a data set that has the same data set that has been processed through t-SNE. And as I said, t-SNE assumes that the distances in the data set are t-distributed, which is not true for the rabbit. Therefore, it distorts the rabbit a lot. On the right-hand side, you get the rabbit processed with our algorithms. And as I said, the local comparisons are meaningful for us. So we are good at preserving local features, such as the ears. They are a very prominent feature in this data set. However, the global features are not preserved as well. Is this important? In my opinion, anyone who has Excel can look at large effects across their data set and look at the global features. So I don't think that is really a space that we need to address here. Compared to other methods, this is again our housing example. So with topological dimensionality reduction, we got this plot that was pretty useful because the things are structured in a useful way. What we get with PCA is this sort of mess, and with t-SNE it's like that. Now, as I was saying before, we can say this is a separate group, and we will find out what are the fundamental drivers of this being a separate group. You can't do that on either of those plots because you can't really see much. And the reason why you can't see much is because with those methods you are not really arriving at what is the fundamental space this data set works in, because the assumptions that these methods make are violated. I would say, in fact, that these assumptions are more often violated than not. So in terms of tools that you can use for this, our main competitor is ISD at the top. The main difference between what we do and they do is we show you all the points that you have in your data set. They sort of first cluster the points and then show you mini clusters, because calculating all of the points individually is pretty damn hard. ISD, which is a software that sells for 100K per one license, is running on a back end of Mapper, Python Mapper, which is a free software. And it's basically the same thing, except that it's very awkward to use, as free things tend to be. And our software is obviously the best option here, but I don't think we have to go too deep in that. So I will start wrapping up here. Yeah, I think I have time for that. What I was trying to tell you was, I was trying to convince you that you need to be able to understand what you are doing with your machine learning models a lot of time, because of human readability that is necessary in certain contexts, justifiability, to avoid discrimination, to avoid feedback loops, to facilitate improvement, and to avoid some of the overfitting. Then I was trying to explain what is exploratory data analysis, why is it a good way how to look at your problem, what is dimensionality reduction and how it aids exploratory data analysis, which is the concept of manifold learning. And I also try to talk a little bit about the topological approach to manifold learning. And I think I have a little bit more time, so I have an extra slide before we get questions. And this is the practical one. So if you can't be bothered to do TDA, what I would suggest doing, just plot everything all the time in as many ways as you can think of. I list some of the ways there. I think what is very useful in terms of understanding what's going on in your neural network is just plotting the weights, showing them as a picture. It will a lot of time tell you what's going wrong when something's going wrong. A lot of time it will tell you how your model actually works. And I would like to point you towards this book by Kathy O'Neill, which is basically just about how machine learning can be dangerous to society. And I think it is immensely important to know this before you embark on deploying machine learning in applications that affect people. So this is the question time. So, as I said, Python Mapper is open source tool, and I'm afraid that that is currently the only open source tool that is there. I would suggest perhaps just trying something like Disney and doing a 3D sketcher, as a starting point, that's like the easiest thing that you can do, like literally within a few minutes, and that can tell you something. Yeah?
So would you be able to maybe filter the topology? Is there like a component you could use that could tell you maybe PCA can do this faster and use eliminate later?
Yeah, well, I think this is pretty hard to find out because you are always, what you are seeing is always data obscured by some random noise. And you don't know how large that noise is. So it's really hard to evaluate whether your PCA is appropriately modeling the data because you don't know what is the residual error supposed to be. So I guess you just got to try it if you want to be really able to say whether there are nonlinear relationships or not. But I really haven't seen actually much success with PCA. It's widely used, but I think it's really fundamentally limited. Yeah? Any more questions? Everything was clear? Yes?
There was a slide contains some useful practical suggestions on like what to do in addition to methodological analysis. Could you perhaps expand a bit on that and just give some tips on how to apply those ideas in practice?
Yeah, so I think understanding your data in terms of like doing just histograms of all the columns in your data set and looking at it is very useful because you will be able to see that perhaps you have some outliers, perhaps everything is concentrated in one point, and these are important things when you are making your predictions. Also, when you start having an idea of what might be driving your predictions, you will get like 2 or 3 variables that are probably interesting. So let's just take those and make a 3D sketcher. And that should tell you quite a lot. You may see, let's imagine just 2 situations. In one, you will see that the 3D sketcher is just kind of a line of points that goes across your display. In the other, it's 2 large clusters. When you see this, it immediately tells you whether you should use something like regression or something like classification. Because if you approach regression problem with classification or vice versa, it won't work as well. And this exercise of just looking at what your problem is can help you. PCA as a first step, it is often useful just to see again if your data set is like really clustered and there are like regions of your data set that are far out. Again, you may want to try to classify that as opposed to do regression. Plot the weights. What you often will see when you just display the weights of your neural network as an image. You will see that there might be stripes, for instance. Some of the variables, of your input variables, will have very large weights, will be very important. Some of them will not be. This can tell you that you can drop some of the variables, and it can also tell you that this one variable has very strong influence over your outcome, and perhaps that is a variable that you, with your common sense, can immediately rule out as being useful at all. So you can find out that your model is actually committing something like that cheese import to, what was it, example, that example from the beginning. And a very similar thing is trying to leave out some variables from your modeling. Just find out what is the effect of taking something out, because that will tell you how much of an influence it has over your results. Basically, the message is just try to explore it as much as possible. Try to uncover the black box. Do we have any more questions? No? Thank you.